Hello everyone, I'm Charles Chege. I'll be continuing with the presentation of the topic game theory. First, we look at the learning objectives at the end of the topic. You expected to be able to define what is game theory. You also expected to understand the possible areas of application of game theory. You're supposed to learn how to solve games with a saddle point, and finally, you're supposed to know how to solve games without a saddle point. First, we look at the definition for game theory. Game theory is a mathematical technique of analyzing and solving competitive situations which arise out of conflicts of interest. Some key concepts, or before we go to concepts, we look at the assumptions that make a game competitive. One, the number of competitors in a game should be finite, say n. So if you're playing a game with two people, then n will be 2. A finite set of possible courses of action should be available to each of n players. You must have the possible courses of action you're to take when you're playing the game. 3, a play of the game will result when each of the players selects a course of action from the set of courses available to them. So you have to select a course, and the opponent selects a course for you to have been considered to have played a game. Number 4, each outcome of a play leads to a set of payments, which can either be positive, negative, or 0. So if the outcome of the game is positive, then the game will be in the favor of the first player. If the outcome of the game is negative, the game will be in favor of the second player. And if the result of the game is 0, then we say that the game is fair. It doesn't favor any of the two players. Key concepts. I'll first go to key concepts in game theory. Number 1, players. These are the competitors or the people who are making decisions in a game. Strategies. These are actions that a player selects for them to be considered to be playing a game. A zero-sum game. This is an important aspect when we'll be solving a game. When we say that a game is zero-sum, whatever is gained by the first player, in addition to what is gained by the second player, has to be 0. Number 4, the maximin minimax principle. This will be the major point at which a person says that they have solved a game. Maximin means that you're going to be taking maximums out of a set of minimums. So we start with the minimum word in the inner side, then you come to the maximum. These will go together with the minimax principle, in which we are going to get some maximums, and then out of those maximums, we are going to select a minimum. So we call it maximin minimax principle. If you apply maximin for the first player, you will apply minimax for the second player, and then at the end of it, you'll compare the two values you obtained from the maximin and the minimax, and then you decide whether you have solved a game or not. So we say that you have solved a game through the maximin minimax principle if you have a saddle point. A saddle point is a point in the game where the maximin value is equal to the minimax value. We look at some managerial applications of game theory. 1, analysis of market strategies, where you're going to sell your goods, your customers, the amount of money you're going to be charging your goods, because you expect that when you're setting the costs of goods or what you're going to charge your customers, you have to look at competitors. What are they charging in the market? Number 2, you can use game theory to evaluate the responses of consumers to a new product. You want to know how your consumer responded to a certain new product you put in the market. What level of influence did the product have in the market? Number 3, decision-making in techniques to increase market share. You might be having a product that you have sold over time, and now you want to check whether maybe changing the branding, changing the quality of the product has had an influence in controlling the customer base you have in the market. Then material procurement process. The process of procurement has several stages and some requirements. You may be wanting to know what minimum level of stock should you have for you to reorder? When to reorder in such things, you can use game theory to make such decisions. Then, lastly, you can use game theory to determine or examine new business ventures. Just before you venture into a business, you need to know what is the expected profit. What are the costs we are likely to incur? What are other people who are in the same business as we want to go in? Such decisions before you just introduce a product or you venture into a project can be determined using game theory. Now, we need to formulate a situation that can be considered to be a competitive game. We've talked about players. So we will have two players. In this game, we have player A with strategies. So strategies for player A are 1, 2, 3, and 4. We have the opponent, player B. Player B will have strategies Roman 1, Roman 2, Roman 3, and Roman 4. This is a 2 by 2. Why? We have two players in the game. It's a zero-sum game because we are assuming that if player A gains 1, player B loses 1. That is 1 plus minus 1, which is 0. And that is the basic assumptions for us to be able to solve this game. Now, we have said that if you are solving this game, you need to get a saddle point. So how do you get a saddle point? This gets us back to the maximin, minimax principle. We will apply the maximin, minimax principle in the whole of this game by applying the first part, that is maximin, to player A and minimax to player B. So if we consider the strategies selected by player A, if player A selects strategy A, then they can gain 1, lose 6, gain 8, or gain 4. If they select strategy 3, they can gain 5, lose 1, and they can remain in the same financial position as they were before. So let's first get the maximin value for player A. We'll do that by getting the row minimums. Going back to our matrix, row minimums, these are our rows. So for each of the 4 rows, we get the minimum of each row. In this row, it's 6. This one is negative 6, negative 8, negative 5, and negative 4. Then we get the maximum out of those minimums. So find row maximum, these are the values. Then find the maximum out of this set of minimums, which is negative 4. Negative 6, negative 8, negative 5, negative 4. The maximum out of this set is negative 4. Then for player B, their strategies are based on the columns. So we will apply the minimax principle for player B. Get the maximums, then out of those maximums, we get the minimum. Therefore, out of 1, 3, 5, and 3, we get the minimum, which is 1. Out of negative 6, negative 7, negative 5, negative 4, we get the maximum out of that. In this case, we will have 5, we will have negative 4, we will have 8, and we will have 7. Then out of that set of maximums, we get the minimum. For player B, the column maximums are 5, negative 4, 8, and 7. Find the minimum out of that set of minimums. The minimum here is negative 4. So again, for player B, the minimax principle gets us at 4. Meaning, the value we get for player A by applying the maximin is the same as the value we get for player B by applying the minimax principle. And that point, we now have a saddle point, which corresponds to this. So this is the point where we have a saddle point, because for both players, we have this as the meeting point. Now, the value at the saddle point is called the value of the game. So if you do maximin and minimax and you get the same value, that means that the game has a saddle point. So the saddle point is at 4. For you to have solved the game, there are several things that you need to come up with. Number 1, after getting the saddle point, give the value of the game. Number 2, give the optimal strategies for each player. coming back to our matrix, this value -4 exists where the strategy for player A is strategy 4, and the strategy for player B is strategy 2. And therefore, the optimal strategies, the strategies that will enhance that the players win the game are, for player A, strategy 4. For player B, strategy Roman 2. Since the value of the game is negative, then we can conclude that it's in the favor of the second player. Note that if the value of the game is positive, the game would have been in favor of player A. If the value of the game is 0, then we say that the game is fair. We can look at an example. We have 4 strategies for player B. For player A, in this case, we have 5 strategies for player B, with this matrix representing the payoffs for each player. Now we will apply again the max-min principle for player A. That is get the maximum, or rather, sorry, the minimum of each row. From here we can see that the minimum for the first row is 7, then for this one is 20, and so on. Then for player B, we use the minimax principle. Get the maximum, then obtain the minimum out of those maximums. So for the columns, the maximums are 25, 35, 20, 28, and 30, as listed here. Then the minimum out of this set of maximums is 20. Therefore, again, we have 20 being the saddle point. So that from there we can be able to tell that if the game has a saddle point at that point, then the value of the game is 20. The optimal strategies for player A is 2, the second option, and the optimal strategy for player B is Roman 3. And the game is in favor of player A because the value of the game is positive 20 compared to the illustration where we have a negative, and we concluded that the game was in favor of the second player. Now, sometimes you have games where you can't get a saddle point. Such games are a bit complicated, but we'll consider where we have a 2x2 zero-sum game to make illustration of such problems easy. Now, consider this game. Player A's strategies are 1 and 2. Player B's strategies are Roman 1 and Roman 2. With these payoffs, we notice that all of them are positive, but that is not a problem. We can be able to detect and be able to solve the game if it has a saddle point. So we apply max-min for player A. We get row minimums first. Minimum for this row is 3, minimum for this row is 2. Maximum out of this set is 3. Then we go to player B. Get column maximums. Maximum is 4. Maximum for this column is 5. For this column is 5. Get minimum out of those maximums. The minimum between 4 and 5 is 4. And therefore, since this value and these are not equal, then we conclude that the game has no saddle point. So how would we go about solving a game where the value we get for player A is different from the one we get for player B? We have to apply a strategy in probability theory called expected value principle. Under the expected value principle, the expected value of a random variable x, the random variable x can be a value that has been obtained from a random experiment. So for a variable to be considered in a probability theory example, it has to have some associated probabilities. So if you know the values of x, and you know the corresponding values, the corresponding probabilities for each values of x, summing the x's multiplied with their corresponding probabilities would give you the expected value. We can do an example to illustrate the principle of expected value. Consider a game involving tossing 3 coins. You toss the first coin, the second coin, recording the observations we make, you take of every toss. Now, we know that a coin has 2 sides, the heads or the tails. And the probability of any of them showing up is a half. So if a player gets 3 tails, they are penalized 10. So a penalty of 10 will be considered as negative 10. If they get 2 tails, they gain 2 shillings. If they get 1 tail, they gain 0 shillings, and 5 shillings if they have no tail. The question is this game worth playing? To answer that question, you have to calculate the expected value. If the expected value is positive, then the game is worth playing. If the value of the game is 0, then you can take chances, but you don't play a game where the expected return is negative, because it means that you will be losing in that game. So let's look at the solution to such a problem. One, you have to ask yourself, how many possible outcomes would I get in tossing a coin 3 times? You can have 3 heads, you can have a head, followed by a tail. You can have a head, a tail, then a head. All these of them, which are 8 of them. Now, we can come up with a table illustrating this. Number of tails we can get, as we've seen above here. You can have 3 heads, you can have 2 heads, you can have one head, or you can have 2 tails. If you are considering the tails, you can have 0 tails, 1 tail, 2 tails, or 3 tails. Now, the table is based on what you get for every outcome. Number of tails, you can have 0 tails where you have head, head, and head. You can have 1 tail where you have only 1 teeth. You can have 2 tails when the 2 teeth are 2, or you can have 0 tails when you have no tail at all. In the case where we have 0 tails, there was only 1 outcome, and that is the first case here. In the case where we have 2 tails, we have 1, 2, 3, a single tail. In the case where we have 2 tails, this is 1, 2, 3 again. And lastly, when we have 3 tails, we have 1 case only. So the return of the game, we had been told that a person gains 5 if they have no tail at all. They gain nothing if they have 1 tail, and they gain 2 if they toss the coins and they get 2 tails, and then they lose 10 if the tails are 3. Corresponding probabilities. Out of the 8 cases we saw in the sample size, or the sample space, this is the sample space containing 8, only 1 of them didn't have a tail. And that's why out of 8 we are picking, we are picking 1 out of 8 to represent the case where we have 0 tails. When we have 1 tail, those were 3 cases, so 3 out of 8. When we had 2 tails, those were 3 cases, and then when we don't have a tail, that is 1 case out of 10. The most important thing to note here is that when I sum these probabilities, 1 over 8 plus 3 over 8 plus 3 over 8 plus 1 over 8, that is 8 over 8, and therefore the summation of the probabilities in this case is 1. So we said, for you to get the expected of a random variable, you take the x's, you multiply with the corresponding probabilities. So I would take this times this, plus this times this, plus this times this, plus this times this, which are listed here. And then that gives us this, which is 1 over 8. So since the expected value of the game is positive, therefore, this is a game worth playing. We are going to apply this concept in solving a game without a saddle point. Look at this game compared to what we had when we had 2 strategies for each player. I want us to represent it in general form as A, B, C, D matrix. Now, if player A selects the first strategy, that means player B will gain A or B. So for us to be able to solve this case then, we have to find probabilities associated with B gaining this and B gaining this. So we will assign P, so that because we have only 2 options, if player B gains A with probability P, then they gain B with probability 1 minus P. Because we've already said in a certain situation, the summation of the probabilities should be 1. So if I put P here and I have only options A and B, then this must be 1 with probability 1 minus P. This is the case here, that if player A selects the first strategy, then player B earns payoffs A and payoffs B. A with probability P and B with probability 1 minus P. So since I have payoff and corresponding probabilities, then I can calculate the expected payoff. The expected payoff is probability times the payoff. For A, A times P. For B, B times 1 minus P. Opening up the second bracket, you have AP, there is 1, then B times 1 is B, then B times P is BP. Then we have to go to the second strategy for A. Ask ourselves, if A selects second strategy, then B gains C with probability P, and D with probability 1 minus P. Repeat that. If player A selects strategy, the P and C with this, so we can get the expected payoff to be PC times D 1 minus P along the row. So that when we open the bracket, we get this. We should note this. Since the game is considered to be zero-sum and fair, then we are going to assume that whatever expected payoff we get in A and whatever expected payoff we get in the second option, they should be equal. So we had two options when A selected this strategy and when they selected this strategy, and for it to be a 2-by-2 zero-sum fair game, what result we get here and what result we get here, they must be equal. And therefore, we will equate what we got in the first strategy to what we got in the second strategy. This is the case. Now, we have to come up with an expression for P and an expression for 1 minus P by making P the subject of the formula in this case. This will be done by first getting like terms together, these and these, then making P, or rather factoring out P, and then you can take these and this, factor out P and bring them to one side and then bring B to this side. Then factor out P because these will have P and these will have P. Then divide both sides by this factor minus this factor so that you remain one side with P and this will be P. Then 1 minus P just implies this. Then you can get the LCM. You can put 1 over 1 then get the LCM is A minus B. You can see here. While opening the bracket, this is negative C minus D. It's up to here. Then minus will make this B plus. So that we have 1 minus P is this. You have again to do that for player B selecting different strategies. We know that player B is selecting strategy Roman 1 and Roman 2. So we can change so that the probability of A winning any of the payoffs A and C is R. So that is 1 minus R. Repeat the procedure done in B so that you will get an expression for R as derived here and 1 minus R. You see that we are making the same assumptions we made for player B, or rather for player A. So that you have the expressions for R and 1 minus R. Then we can go back to our example. Remember, in the general case, 3 is A, B is 5, C is 4, and D is 2. So we can get the value of P from the expression. P is D minus B, then A minus B minus C minus D. Replacing them here, we get P is 3 over 4. Then we can get 1 minus P is 1 minus 3 over 4, which is a quarter. Then the expected payoff from the original expression is A times P, which is this. We get 3.5. Or equivalently, you can select that it's the other strategy selected by A. So we have P, C, then D 1 minus P. Again, you get 3.5. Something important to note is that we are getting the same value for each case. Again, if we consider strategy selected by player B, you'll notice that we can get R is D, C, A minus C, B minus D, which you get a quarter. Then 1 minus R is actually a half again. Applying in the same expression, A times R plus C 1 minus R, you get 3.5. The other alternative, the second strategy, you get again 3.5. So at least we know that the expected amount a player can get from the game is 3.5. And that makes the value of the game. The value of the game is 3.5. So we can make a conclusion. Which player is being favored by the game? It's player A, because we said if the value of the game is positive, the first player is favored by the game. If the value of the game is negative, then the second player is favored by the game. And the game is fair. Anyone can win if the value of the game is 0. So in this case, player A is being favored by the game. But note that this is a game of pure strategy, because we don't have a certain strategy that is optimal for any player. Any player can choose any strategy, but the expected winning amount for the game is 3.5. This is an illustrative example, and the expected result is a half. Of course, we'll expect that A is -11, B is 5, C is 7, and D is -9. Applying the formulas that we have derived above there, you'd expect P to be a half and R to be 7/16. You have to calculate both P and R, regardless of whether the value of the game for every strategy selected by the player is the same. It will act as a means of identifying whether you have made an error in the derivation. Lastly, we can do a learning outcome self-assessment question. One, can you be able to tell what is the value of what is game theory? Can you define game theory? Can you be able to solve a game? What will you be expected to do for you to be said to have solved a game? Number one, get the saddle point using the minimax max-min principle. Number two, find the optimal strategies for each player, then determine who is being favored by the game. Those 4 points are important. Then, what is a saddle point to a game? What are assumptions that a game should have for it to be considered to be competitive? Then, what is the expected value in probability theory? Then, how can I apply the expected value theory to solve a game that has no saddle point? Thank you.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then, email all the above to apply@mku.ac.ke.